Hello, so in this video I'm going to talk about chain rule. Now, chain rule, what it does is it starts with a set of two functions. So we start with, for instance, the equation or the function y equals to f of our u. Then we have g of x. Well, that's equal to u. So what this does is it tells us that we have a composite function f of g of x. Okay, so most people recognize this as a type of composite function. Okay, so we have a composite function. Now the question becomes, for instance, like if we wanted to know what the derivative of the composite function happens to be. Okay, so in that case, that leaves us with a big question. Just how exactly do you find the derivative of a composite function? Now, let's say, for instance, that we want to start by just considering the function y equals to, let's say, u. Well, let's do it like this. Okay, so how about we have the function or the equation y equals to u squared, and then we'll just say that u is equal to, okay, so we'll just have to write an equation right here. So what we'll do here is we'll just say that, for instance, that this is equal to 2x squared plus 3. Now, what this means is that we have that the equation y equals to u squared is going to be written as y equals 2x squared plus 3 and then square that. Now, we know that we can take the derivative by probably just, expanding both terms, but you have that now we can use what is called chain rule. And even though we haven't really said what chain rule is, this is the way that we look at it. So let's say that we want to find dy dx. Well, notice that if we look at the original two equations, u squared and u equals 2x squared plus 3, well, the way that normally that we might write it is in the following manner. You take the derivative of y with respect to u, so you end up with dy du. Then you take the derivative of u, but with respect to x, so that gives you the following. It gives you du dx. Now, interestingly enough, when we multiply these two, this is going to give us our derivative of y with respect to x, but the only issue is that you would end up having to substitute respectively. So let's go ahead and look at how we can find the derivative of y with respect to u and then derivative of u with respect to x. So that means that, okay, well, we just need to find dy du, which dy du is equal to 2u. But then if we look at, for instance, du dx, du dx is equal to 4x. Okay, so that doesn't seem too bad. So what comes next is that we would go ahead and say, well, okay, that means that dy dx is equal to, well, dy du is 2u, and then du dx is equal to, well, 4x. Okay, so in this case, the way that we look at it is that we just need to go back and substitute whatever u was equal to. So we have that that'll be 2 multiplied by 2x squared plus 3, but multiplied by the 4x, which means that this is equal to 8x multiplied by 2x squared plus 3, and then that would be it. Now, this seems somewhat a little challenging, but it's actually not that bad. And imagine having to expand 2x squared plus 3 to the second power. I mean, while you can do that, I mean, you really don't need to in reality. So yeah, that's just something to think about. Okay, well, if that's the case that we can use this type of notation, then why don't we do just one more example and then we'll just move on to the most traditional sense of chain rule. So we have that, okay, let's say that we have y equals to the square root of u, but then let's say that u is equal to t squared plus 1, but then let's say that t is equal to, let's say for example, okay, so let's say that for example that's going to be perhaps like x plus 1, okay? Now, notice that if we want to find dy, dx, well, notice that you're going to have probably multiple chains. For that matter, what we'll do next is we'll just say find the derivative, and we'll just say and dy dx for when x is equal to 1. Okay, so that's going to be not too bad, but it's going to require quite a bit. So here's what we'll do. Okay, so accordingly, we need to find, according to our short method of chain rule where we just multiply each derivative. So we have dy dx is going to be equal to dy du, but then that's going to be multiplied by du dx, not dt. Then that's going to be dt divided by dx. Now, note that you have multiple derivatives in this case that you have to find. So, for example, dy du, okay, so dy du, dy du, if we go and we use that this is u to the 1/2, that's going to be 1/2 u to the negative 1/2, which is equal to 1 divided by 2 times the square root of u. Furthermore, we can find du dt, which is equal to 4t. But then we also have that we can find dt dx, which is equal to just 1. Okay, so that's actually not too bad. But we'll go ahead and form the product of the three. So we have dy dx is equal to 1 divided by 2. Now it says u, but we're going to have to substitute u, but it also says that you end up with a t, so substitute naturally the x plus 1. So what that's going to look like, it's going to look a little weird, but it's going to be, let's see, x plus 1 squared plus 1, and then that should be it. Okay, so we have that that's going to be multiplied by du dt, but du dt has to be written in terms of x. So let's see, what did we get for du dt? We got 4, but what is t equal to? T is equal to x plus 1. And then we're going to multiply this times the derivative of dt dx, which is just 1. So what this ends up being is the following. It ends up giving you 4x plus 1 or divided by 2, the square root of x plus 1 squared. And then we have, let's see, plus 1. Yes, okay. Now note that the 2 cancels out, so that's going to be 2 times x plus 1, and this is all divided by the square root. Okay, so we have that that's divided by the square root of x plus 1 squared plus 1. Okay, now I might agree that, yeah, that looks a little complicated, for instance, but let's just look at it like this. If we would have wrote dy dx, or let's just say like if we would have just wrote y, then what y would look like is the following. You'd have that y would be equal to the square root of x plus 1 to the second power plus 1, and then from there I would just take the derivative of this. Now you'll be able to essentially say that, okay, well, that's really just x plus 1 squared plus 1, and then all to the 1/2. The question here becomes, okay, but let's see. The question really becomes like, how do we find, let's see, du dt is actually, yeah, there's a mistake right here. This should actually just be a 2. Which means that that's going to be a 2 also. Okay, I'm glad that I'm kind of looking at it and seeing what's happening. So that should be a 2 also, which means that the 2 is completely gone. So we have that that's going to be 2, and then that 2 cancels out entirely. Okay, so the whole point that I'm trying to make here is that once we kind of get a view of, like for example, like what does the composite function look like, then in that case that'll kind of allow me to figure out what the derivative is. So we have that this function right now is in terms of x. So what that means is that you'll see that the derivative of this is actually not too bad, but you got to get you have to kind of get used to like the chain, applying the chain. So we'll probably have to come back to this one where we try to find the derivative of it without using the composites. Let me see. Okay, so let's go back to our original question, how we're just going to find the derivative at 1. So notice that in this case we have that the equation dy dx at x equals 1 becomes 1 plus 1 divided by the square root of 1 plus 1 squared, and that's plus 1. Now this becomes 2 divided by the square root of, well, 1 plus 1 is 2, squared is 4, plus 1 is 5. So I have that this is going to be 2/5 times the square root of 5. Now, one thing that you can probably say is that if you would have probably just said that we didn't need the derivative of each one of these, you probably could have just figured out, like, for example, like what is u, what is t, and then, yeah, well, ut. Okay, so that means that t is equal to 2, but u is equal to 5. So you're actually just plugging in 5 into dy du. Um, That is one way to do it, but if you don't want to do it that way, that's totally fine. You can do the composition. So our next thing that we can show you is that we look at the formula, the most traditional formula for chain rule. So let's go back here. So we know that, if we're taking the derivative of a composite function defined in the following way, so we have that this is f of u and this is u equals to g of x. Now, similarly, I can say that dy du or dy dx is found by finding the derivative of f but with respect to u and then multiplied by let's see. Um, okay, so actually, let me change this to the variable y. That way we don't get confused. So this will be derivative of y times the derivative of u with respect to x. Now, what this means is that basically we know that that's going to be f prime of u multiplied by, well, in this case, that's going to be g prime of x. But what this means is that this becomes f prime of g of x. And then you have that that's multiplied by g prime of x. So my derivative of my composite function is f prime of g of x multiplied by g of x prime. So we could probably just clean this up a little. So like for example, like if we know that we're taking the derivative of a composite function like f of g of x, then I know that this is going to equal f prime of g of x multiplied by g prime of x. So it's the exact same thing, but let me just go ahead and add one more thing to it. So what most people tend to say is the following. They'll use something called outside, and then they'll say like that you have inside. Because basically the way that I look at it is that f prime is the outside and g of x is the inside. So you're always differentiating the outside inside. So it's always the outermost parentheses, which means that you should be able to figure out like what the derivative of this is. So try to do this derivative and try to see like that you get the exact same thing right here, where you get x plus 1 divided by root x plus 1 squared plus 1. Okay, so let's try an example. So in an example, a typical question that you might see in class or like on a test or whichever, you might see that, okay, well, let's say that we're taking the derivative of the following. We have, let's say, 1 divided by the square root of x squared plus 1. Now, to find the derivative of this equation, basically you have to look at it as you have that there's an outermost function, which in this case, you would first actually need to rewrite it, to be honest. So like you have x squared plus 1, and then that's to the negative 1/2. Now, here's where, you can use chain rule. So the outermost function is the parentheses to the negative 1/2. So what that means is that you're going to have applying power rule. So you have 1/2 multiplied by x squared plus 1 raised to the minus 1/2 minus 1 multiplied by the derivative of x squared plus 1. But that gives you the following. It gives you negative 1/2 x squared plus 1 to the negative 3/2 multiplied by, well, the derivative of x squared plus 1 is just 2x. So this gives you Okay, so let's rewrite this as negative 1/2, and then you have multiplied by 1 over x squared plus 1. Okay, so x squared plus 1 to the 3 halves. And all of this is multiplied by 2x. Now, when you go ahead and you simplify this even further, okay, so if you simplify this even further, you'll find that basically you get negative x divided by x squared plus 1 to the 3 halves. I don't like that. Okay, so that should be that, and that's to the 3 halves. So this would be the derivative of that equation, or not equation, but expression. Okay, so in this case, like I see that there's many different things that I can do with this equation, um, in terms of like just rewriting and cleaning it up and all that kind of stuff. Okay, so how about we look at an example where we have that it's going to be somewhat similar. So like if we have negative 2 divided by x plus 3, and this is to, let's say, like the third power. Now, let's say that this is y equals. Okay, so if we want to find like dy dx, well, this is more or less the exact same thing, essentially. You have that you just need to rewrite the equation that way so that it's in the format that you're feeling most comfortable with, like negative 2 times x plus 3, that's to the negative third power. Now, in this case, note that this is easy as respect to the chain rule, where you just say that, well, I have that this is y prime equals to, so we treat this as it has the outside. So we have negative 2 multiplied by negative 3, x plus 3 to the negative 4, multiplied by the derivative of x plus 3, because that's the most interior of the equation. So you have that reduces down to the following: 6 times x plus 3 to the fourth power multiplied by 1, which negative 4, sorry. So that means that your answer is 6 divided by x plus 3, but that's all to the fourth power. Okay, so in this case, this gives us how we can find the derivative of a constant time divided by a divided by a function. Now, it's not possible technically to use reciprocal rule. I mean, I guess it could be, but in this sense, you're still using chain rule no matter what. Okay, so just be careful with that as it relates to, finding the derivative of these guys. Now, I want to do like one more, just a few more examples of like how we can apply chain rule. So, for instance, let's say that you have a uh, you have an equation where you have x plus 5 raised to the fourth power, and let's say that this is multiplied by okay, so let's say that this is multiplied by a quadratic equation such as like x squared plus 5x plus 6, but this is raised to the, say for example, second power. So if we want to find, let's say for example that we want to find just the first derivative, like y prime, we can do that. Okay, so we can do that because we know that basically this is just product rule. So we just need to apply product rule and also chain rule. So apply product and chain rule. Okay, so in this case we have that, well, the derivative of x plus 5 to the fourth power That's going to be 4 multiplied by x plus 5 raised to the third power multiplied by x squared plus 5x plus 6 raised to the second power plus, okay, so now we have x plus 5 to the fourth power, but this is going to be multiplied by 2 times, we could say 2x plus 5, and let's do this. Okay, so 2x plus 5, and we're going to multiply that by x squared plus 5x plus 6. Now, this 2x plus 5 came from the derivative of the x squared plus 5x plus 6. I mean, you can write it in the back, but it's fine. Now, looking at this, it looks a little crazy. So what we can do is we can take out the 2, take out the, let's see, 2, and then let's say that we take out x plus 5 to the third power, and then we take out the x squared plus 5x plus 6. Okay, so what gets left behind in the parentheses essentially is the 2 times x squared plus 5x plus 6 plus, okay, so we took out a 2 here as a greatest common factor, and we took out the, yeah, let me see, and then we took out the x plus 5 to this third power. So what that's going to leave behind in the parentheses is basically just the 2x plus 5 and then multiplied by the x plus 5. Okay, so unfortunately we have to reduce this as best as possible. So that's going to be 2 times x plus 5 raised to the third power multiplied by x squared plus 5x plus 6 and then multiplied by 2x squared plus 10x plus 12 plus 2x squared plus 15x and then plus 25. Okay, so I got that by foiling, so that gave me 2x squared plus 10x, then that gave me 5x, which is 10x, plus 25. So now we have to go through the process of reducing this as best as possible. So we end up with 2 times x plus 5 cubed multiplied by x squared plus 5x plus 6 multiplied by, okay, so that's going to be multiplied by 4x squared. So 4x squared plus 25x plus 25. Okay, so potentially this is our solution as long as we did our work correct. Okay, so this is our solution, and I don't think that it factors in any way. Okay, so we'll just leave it like this. Okay, actually there's a mistake right here. That's right here. Yeah, 12 plus 25, that's 37. So that should be 37. Okay, now what I want to do in this last example is to work with, okay, so this one was product and chain rule. So let's say that we have the following function, f of x equals to x divided by x plus 1 raised to the second power. Now, there are several ways that you can, rewrite this equation. For instance, you could write it as x squared divided by x plus 1 squared. And, yeah, okay, that's going to be quotient rule. But let's say that we want to find, f prime of x. And then we can say that we want to find f prime of 1. So the way of which that we're going to do this is, notice that we have an outer function and we have an inner function, but then it's a quotient. So that means that we're going to have to use chain rule and quotient. Okay, so what that means is that, okay, so we go ahead and we look at the outermost function. So that would be the f prime, or the outer function, sorry. So f prime of x is equal to, okay, so we have 2 multiplied by x divided by x plus 1 to the first power multiplied by the derivative of the interior, which this is where we get the quotient rule. Now, okay, that means that we have 2, we can say 2x divided by x plus 1. So we multiply this by the quotient rule, so we have that we're going to have x plus 1 to the second power. Then we have x plus 1 multiplied by 1 minus 1 from the derivative of x plus 1 times x. Now note that the two x's do cancel out. So we have that's equal to 2x divided by x plus 1 multiplied by, well, okay, so you can see that when this becomes x plus 1, that the x's will cancel out. So what that means is that you have that this is just divided by x plus 1 to the second power. So rewriting this, you get 2x divided by x plus 1, but to the third power. So this is what we get for the derivative of our function f of x. Now, we still need to evaluate at 1. So that means that f prime of 1 equals to 2 times 1 divided by 1 plus 1 cubed, which is 2 divided by 2 cubed, which is really just 2 divided by 8, which is equal to 1/4. So we have that the answer is also 1/4 as it relates to the slope of the tangent. Now if we wanted to, we could probably look at, for example, like the slope of the tangent and also the tangent line. But yeah, we didn't really need to find that, but do note that, yeah, you can find the tangent line if you wanted to. The thing that I observed was that not only can this function be derived several different ways. So like, for example, you can rewrite the function f of x as x squared divided by x plus 1 squared. And then, of course, you can furthermore say x squared divided by x squared plus 2x plus 1. And you would just be using quotient rule. But the one thing that I did observe was that f of x equals to x divided by x plus 1 to the second power. Well, that can be rewritten as 1 minus 1 over x plus 1, and all of this would be squared. Now, the reason of which that I'm saying that is that basically you can apply still the chain rule, but it would be a lot faster in the sense that if you remember how, like, we can look at this and say that the derivative of this is just well, it's just positive 1 over x plus 1 squared. So right, so that means that we have that if we take the derivative of this equation, let's see, what did we get for that one? We got 2x. So let's see, plus 1 minus 1, so that's going to be just 1. Okay, so we still take the derivative of this guy, so that would be 2. So yeah, f prime of x would equal to 2 times 1 minus 1 over x plus 1, and that would be to the first power, but then multiplied by the derivative of 1 minus 1 over x plus 1, which is simply just, it's using reciprocal rule. So we have that this would be equal to 2 times x over x plus 1, just to the first power, multiplied by, so the derivative of this is going to be negative the derivative of x plus 1 divided by x plus 1 to the second power. But this is equal to 2x divided by x plus 1 to the third power, which essentially is the exact same thing, but just using a different method, or approach for that matter. Okay, so some takeaways from this section is probably that you need to realize that, one way of finding the chain rule is by using the product of all of the variables with respect to like whatever they are. So like, we said dy du multiplied by du dx, but we also had what was called the inside outside. Okay, so look at some of the homework questions and be sure that you work through some of those. Some of the examples might be a little bit different, like they might ask for like f of g of 0 or 1 or 2 or 3. Similarly, the same thing for like when you're finding the derivatives at specific values. But that's kind of what I did here in finding f prime of 1. So essentially, you're just substituting once you find the derivative.